And so our next speaker will be Jan, which doesn't need an introduction, I guess. So you will not be introduced.
Okay. All right. Okay. Hello, everybody. It's a wonderful set of talks. And with the microphone on. So yeah, what should I talk? So this is a session about the 20 years of DLS and looking forward, and I think I'm going to look back, if that's okay with you. So the point, the goal of my presentation is mostly to talk about those who are starting research and who have heard that this field is going away, that you have to be engineers, and that it's really, really hard to publish, right? So sort of all these encouragements should, make your heart warm. So I tend to disagree. I think dynamic language research happens. It happens to everyone, even good people. Fundamentally, I'm a good person. I want peace. I love love. And I believe that static types will save the world. Yeah. And I worked on a variety of things. So, ranging from, what does it say? Ownership types. I did a bunch of language implementation compilers, some garbage collection, some transactional memory, some gradual typing, and even spent about good 10 years working on real-time and embedded systems. Let's take a more numerological view of all this. I've had my hand in about 140 publishable units. This is how we count in my world. And out of these, if we sort of do a rough sort of separation, bucketing, Trump-style accounting of them, could say that most of my work is in language design implementation, but, quite a lot is in static types. See, I told you I'm a good person. On a day-to-day basis, I have programmed in Pascal, C, C++, Java, Rust. Pointedly, I have never programmed in Lisp, in Smalltalk, in Lua, in Ruby, and God forbid, Python. Java maybe is the most dynamic language I've used sort of like day to day. And it's a very dynamic language. It's got eval. You can load new code at any time. You can do reflection. So don't discount its dynamics, but still. Yet if you go to my DBLB page, you'll find that quite a lot of my papers relate to dynamic languages. So dynamic language happened even to a good person. So what I would like to do now is spend a few minutes just sort of telling you how and why. And mostly, like the rest of the talk, this will be anecdotes. I hope that they can be useful and amusing or so, but mostly anecdotes. No deep thoughts to be found here. Don't worry. I'm the last thing before lunch, right? So how did I get into this field? So if you think over the years, in the 1990s, when I was a young pup, I'm still young, but not a pup, I started publishing. My very first published paper was actually static analysis of PostScript. The language in your printer, which is dynamic, very dynamic. And that was complete random chance. My advisor said, "Hey, we could do an abstract interpretation of this thing." And okay, why not? Then the next bit I actually picked, and this was following Olling Shiver's work on control flow analysis. I thought, that's for functional languages. Maybe we could do something for object-oriented languages. They're not that different. So I sort of wrote a paper on that, and that was fun. I liked it. I was thinking Smalltalk at the time, but I never programmed in Smalltalk, remember. I'm a good person. So, and the last thing I did in the 90s was to work on how to implement these languages. So there I was doing message dispatch implementation, and the target was Objective-C, but I never programmed in Objective-C. Then we switched to the 2000s. So there I spent a whole lot of time implementing Java for embedded systems. So Java is a dynamic language, but yeah, that's not the most dynamic setting. And towards the end of that decade, I somehow got in contact with IBM, and they wanted to develop a new language that would bridge scripting and programming, and we called that language Thorn. And so we did a bit of work on that, but yeah, so that was a fairly static decade. Then things got more interesting in the 2000s. So in the 2010s, we pushed on that Thorn language, and we actually had that question in mind about those types that lie. So we had types that don't lie, which we called concrete types, they're real, and we had the like types, which we called like types, which were these aspirational types. And then a little bit later, sort of pushing on that same direction, I hooked up with Matthias Verleisen at Northeastern, and we wrote a paper that showed that most of the academic research in gradual typing was hopeless. And both of these got into POPL, and that was so fun. I thought about just putting one Greek letter somewhere just to no, but no. So then the work on Thorn kind of died because IBM pulled the plug, and so I switched over to looking at different languages, and it was good because the question I wanted to answer was, well, why do people need dynamic languages anyway? What is it they like to do with them? And that led me to analyzing large corpuses of code. And where did you find larger corpuses of code? Well, with JavaScript, right? Any website has code and it's runnable, so you can run it, dynamically analyze it, and start to understand what it is people do. And that was a long set of papers, very interesting. And like the answer is mostly they'll do anything. A lot of time it's good. Well, no, let me admit it. Some of the times the crazy stuff is good. A lot of the time it's just mediocre laziness and so on. And then I decided that I needed to work on a language where there was actually a chance of helping people I cared about. So I picked the language R, and I started looking at R as an object of research and working on it. And then the last few years, well, we keep doing work on R, and there is even a paper at this UPSLA on RJIT. And we also looked at Julia. Julia is a wonderful dynamic language in which there are more type annotations than in Haskell. And as a side note, we found out that the subtype relation is not decidable, which is like a lot of fun. When you have a dynamic language whose subtyping can't terminate on all inputs. So, all right, so that's sort of the breadth of it. Now what I want to do is tell you a little bit how, sort of philosophically, how one can approach doing research in dynamic languages, especially when one doesn't really use dynamic languages most of the time. And for this, I'll tell you an anecdote about Northeastern. So at Northeastern, every year we have a session where new students come to meet faculty. And we present ourselves, try to sort of show ourselves in the best of lights. And usually Olin Shivers starts, and he talks about purity and elegance. Doing research in PL is to, I'm trying to get this right, is to strive for true beauty of expression. And usually I come a bit later and I say, yeah, I'm an ambulance chaser. I'll come after the wreck, try to pick up the pieces that are salvageable. That's been my approach, and it works. The uglier the language, the warmer my heart feels. So why reject purity? Purity has a lot of positives, but it usually means you're building things ex nihilo. So we try to do that with Thorn, and one, it's a lot of work, which I always try to avoid, but even if you succeed, which we didn't quite, but even if you succeed, how do you evaluate your success? How do you know what you have achieved, right? The point of a programming language is to help people express their thoughts. If you have no users and no programs, how do you know that you have helped anybody? So, and that's a real problem, right? I mean, if you think about doing a new language, my point to my students is always, what is your experiment? What experiment are you going to have in the paper that will convince the dreaded reviewer 3 that this is worth publishing? So what I've done in my career was to always try to say, well, what's something that is used by real people, and what are the real problems they have on a day-to-day basis, and can we do something to help? Ambulance chasers. So let me illustrate this with some work we did on JavaScript. So at some point we had this idea of what do JavaScript's program really do? So we took a lot of websites, we sort of somehow had analyses that showed what people were doing, and one of the things we noticed was that the behavior on websites, real code, was so different from the behaviors people had on benchmark. So this is about 2009-ish. And so these graphs, I'm not going to explain them in more detail, but just to say on the left, you have the Sun Spider benchmark. On the right, you have the Google website at the time. And let's just say one or two things. So the yellow thing, the yellow color suggests, so the idea is these are over time what you do to an object, sort of a summary of the life of objects. And the fact that it's a big square box means that objects live for the whole application. They never die. In the Google site, over time objects disappear, so you see this sort of gradual tapering off. The other thing in Sun Spider was that the red spikes here are operations on an object, and especially operations where you add properties. And basically, what happens is you create objects, you add a bunch of properties, and then you read them. Google website, yes, you create an object, you add a few properties, and then you update them. So this looks more like a functional language, this looks more like an imperative language. So we thought, that's funny. If people are using these benchmarks to drive the development of their research projects or industrial browsers, maybe there's something not right. So that sent us chasing down a path where we built a tool to generate benchmarks. And my student Gregor Richard went to Microsoft Research, where he built this automated record replay systems. He implemented the whole thing, he had the paper ready, and then the research side was shut down by production, which said, oh, this paper that you're about to publish, it's not going well with our marketing strategy for our latest doomed browser. So the tool was shelved, the paper was killed, we went home. Learning, sort of one teaching moment. If you work with industry, make sure that you contractually have the right to keep your source code, the one you wrote, and publish the results. If not, but it didn't end too badly. A year later, Mozilla reached out. They wanted the tool, so Gregor went to Mozilla, re-implemented the tool from scratch. We wrote a paper for UPSLA with Brendan Eich, Mr. JavaScript, and Mozilla never used the tool. At least not publicly, I'll tell you why. But Apple, where my student Phil Pidzlow was, did make us think about it. So this is their keynote, and they have Safari, and they have the JS Bench suite, which was, that was the thing we were doing. And so, yeah, we're so good. So what happened? What happened, as the best I can tell, is that, so this is back to this Sun Spider benchmark, and this, the other line is the Amazon website. And what you see here is performance of versions of Firefox, speed up, so higher is better. So we start with 1x, and on Sun Spider by version 3.6, you're going 13 times faster. Really good. And then when we run with our benchmark, and and the biggest discontinuity comes with the tracing JIT technology that was introduced at that time. When you run on real-world benchmark, you're running three times faster, but the tracing makes zero difference. Well, remember, the behavior of Sun Spider had nothing to do with real-world behavior. Right? So you were optimizing for something that isn't real. So one of my research contributions is to kill research directions. Thank you very much. All right. I told you I like mine ugly, but how ugly? So I mentioned I work with R, so let me amuse you with little bits of R. I find them funny. So the first bit of R is not particularly funny. This is just a small detail. R, if I call this function with two print statements, what will I print? Well, I end up printing 0 because R is the most widely used lazy programming language in the world with millions of users, dynamically typed. Yeah, the first argument is not evaluated, the second is. No big, we know laziness. Let me amuse you with something more fun. Here's a function 2, and I give it argument 3. The question is, what will it print? And if you know R, you know that it will print the vector of 3 plus 1 and 3 plus 2, 5, 4 and 5. Now, how do you get there is interesting. So you notice that the function has a variable named C, as it's up for its parameter, but C happens also to be the name of the most widely used function in R, which is the function that creates vectors, and they have a single namespace. It's a dynamically typed language. So how does this work? Well, you get to the first C when you're evaluating, and you have what I call context-sensitive name lookup rules. So you're going to say, this first C is in the context of a call. So I'm going to look my environment, find a definition of C, and check, is that definition bound to a function? If yes, I can call it. But here, it's bound to 3, so no. So I keep going until I find a function. And the second definition of C just finds 3. All good. And here's the trolling part. If I call 2 with bad as an argument, what do I get? Well, I get clearly symbol C not found, so same thing. So what is going on? So bad is not evaluated. So what happens is when I call C, the first C has to be found. I have to, so I look in the environment, I find that's the parameter. Is it bound to a function? Well, since R is a lazy language, I don't know. I have to evaluate the argument to know whether it's bound to a function. As a side effect of evaluating the argument, well, I call bad. And what does bad do? Well, bad, it says, walk your call stack. If you find a variable C in your caller, delete it. All right. My ugly duckling is ugly. Yet, millions of people use it. So another thing I spent a lot of time doing, and I had, it was amazing fun, is actually looking at how these languages are implemented, and more specifically actually implementing them. So spent about 10 years working on Java, and this is a really dynamic language, and then I spent another 10 years working on R. Each iteration, each n in this list, you can assume that n minus 1 was a failure, right? So now we're at this last compiler named Sh. We hope it'll work. It hasn't failed yet. So why is it so hard to implement languages that are dynamic? Let me tell you. So we had a paper at DLS in 2019, and it did a reasonable job of summarizing the difficulty, and its title is enough to actually sort of feel the pain. So say I want to, I have to stay here. So say I want to compile this function in the middle. So it's a piece of code, and it's going to call other functions, and it gets arguments. So in a dynamic language, we have to worry what those other functions will do. Will they add new code? In the case of R, will they delete some of my local variables just for fun? Right? So I'm already sort of stressed out about what this can do. So maybe if I'm calling functions that are local to my package, maybe I can do some inter-procedure analysis and get a good guess that it's going to be safe. Maybe. But then I'm called by somebody. And whoever calls me is sending promises, unevaluated computation. So anytime I read an argument, I will trigger computation. That computation may cause reflection, cause new definition, cause variables to be deleted. So in order to compile a function, not only do you need to know what's below you, but what's above you. So basically, it's like this tangled mess. And unraveling it is what causes your brains to melt. Okay. And it's also an interesting point of the tension between static and dynamic, right? You say this and you say, well, wouldn't it be nice if the programmers could tell us, yeah, but these arguments, they really are not going to delete your variables. A little bit of annotations would be nice. And the problem is, as soon as you start doing that, you restrict the expressiveness of the language. You remember I told you earlier that people do a lot of crazy things, and often these are, or sometimes they're for good reasons. Well, you would lose a number of use cases. And your language would become less usable. And I'll spend one or 2 minutes on usability. How much do I have left? 5? You see? 4. So I'll be faster. So I spent a year working for a startup that was doing some security work, and they had a pipeline where they had 50 Java programs that had embedded strings of SQL that would generate the SQL dynamically, send it to a distributed database, run it on a cluster of 1,000 machines, roughly. So heaven. And the boss said, Java is a horrible language. We have to kill it. We will program in Rust. And I thought, you know that you've hired 600 Java programmers in the last 2 years, yes? You have a plan for training them, yes? No. The reason I left doing ownership types is I was thinking nobody could use this. This is too much of pain on programmers. So basically what they were doing was a big data analysis pipeline. And I thought, well, I could take some of the steps and see how to re-express them. Right now it's Java and SQL embedded. What would it look like in R? Well, this is just an example, but it sort of gives you this idea that I can read two CSV files, I can group them by name and age, I can add a column that has the mean weight, I can join the tables, I can compute, I don't know, my weight times my salary because it's interesting, and return that. Okay? So that's a data analysis pipeline in R. I don't do Python, I've never did, and I will never, but ChatGPT gave me the equivalent Python code. Python code looks like retarded R. It's R from about 10 years ago without Hadley Wickham at the board. So it's okay, you know, but you see there's way more strings. Whenever you see strings, you sort of have to say, yes, this is not going to end well. And then I wrote the code in Rust. Wonderful. It has even more strings. So the Rust code is unreadable, unmanageable, untyped, and slower. So, yeah, usability, it's important. So I'll conclude. So parting thoughts. Well, what I've been telling you is that if you want to do research in this field, think there's 4 things that are important, and most researchers just do the last one. So the first thing is you pick yourself a community that you want to be in. People that are doing something interesting, or people that you like. For instance, in R, I like statisticians. They're nice people. They're not practical, but they're nice, on average. And then you sort of look at what they're doing, and you find what is it they're doing that's bad or painful or that they don't like. That leads you to actual problems that are real-world problems. And then you go and you do the thing that you do, which is propose great solutions, blah, 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 blah. But if you don't do the first 3, you're left to think of solutions. How do you know they will connect? And if you don't have the first 3, how are you going to evaluate your solutions? All right, so thank you very much. It's been a pleasure to talk to you and to sort of misattribute one Kubrick to another. It's full of dynamic languages.
So we have time for a couple of questions.
So funnily enough, we have at least 3 people from the JavaScript team at Mozilla here in the room. And it's actually kind of delightful because as you were starting to introduce this benchmark creation thing, Matt leaned over to me and was like, wow, we should really get our hands on that. And this all happened before our time, but I did think it would be nice to point out that like the web browser community has slowly but eventually come around to the standpoint, and like, you know, the creation of new benchmarks that actually match the real web is something that's being actively worked on this year. So the industry does eventually catch up. It just takes us some time.
My point was not to sort of disparage. My point was one of, you know, sort of more philosophically, how do you find problems? You find by looking at what is happening. And yes, of course, since then, people have much...
Please do disparage. It was, okay. It was correct.
No. I'm a good person.
If you're a good person and you're designing a new programming language, presumably you'll do a static one, right? But you gave that example of what it looks like to do data analysis in Rust. Could you just explain what you believe? Like, what did Rust do wrong? How could you do better? Or should we just use R?
So if you're, okay, so you've packed a lot in a sort of fairly tight package. Of course, you all use R if you're doing static data analysis. For data analysis, it is objectively really the best tool. Now, if you sort of zoom out and say, well, as a programming language, could we have something that has the benefit of Rust? And so why do I like R for data analysis? Because the programming model in data analysis is your programs are irrelevant. The only important thing is the data. Your programs are just there to excite the data, to get a little bit of insight. And you will throw them away 99% of the time. So what you're doing is you're trying things, because you have no clue. You try things, and then you get something. And then maybe you want to deploy it. So I remember Netflix was using R for their data analysis, and then for deployment, of course, you can't use R, so they would recode everything in Java, which is horrible, right? Because now your edit debug cycle is very long. I was told that one of the reasons they had a big failure for their pricing model was that they were testing their code on a small data set in R, and then they deployed it, but yeah. So what you want is both, right? You want to have the types when you care about, when the code is becoming more structured, rigid, like you want it, but you would like to not have the types while you're experimenting. So, to go back to this, is Rust, the right answer? If you could tell Rust, stop checking this file, just interpret it, compile everything else, but this, I really don't want you to bother me with your type errors and your ownership and your borrowing and all of that, because I don't know yet what I'm doing. And then, start. So it's something like, sort of stop getting in the way while I don't know. And when I need you to get in the way, start getting in the way. I don't know how to do that transition nicely. I mean, we've been looking at it with these gradual type languages, but that may be not yet exactly there. So it's still an interesting research topic.
Thank you.
Do we have other questions?
Thank you for the talk. From an industry viewpoint, developer productivity is one of the primary things that companies are trying to optimize for, because that's one of the biggest expenses that they have. Human time is one of the most valuable things you have in a company. And until your talk, I haven't seen anyone actually mention that. We just keep talking about programming languages and how expressive they are, but we never talk about how much time we're saving developers, or how much safety guarantees we're giving them, or how flexible it is for them, or how fast can they develop their software. Would you agree that that's an important thing for researchers to strive for as well?
Oh yes, but it's also the hard thing. Remember, we're all lazy gits, right? We'll go towards the easy answers. The hard thing is, well, I keep bugging friends at Meta that they should publish a paper on their experience with Hack, right? Went from n million lines, because you can't say what n is, to n times m million lines of code, while gradually tightening the screws. What worked? How did they get there? What were they? There's like a wealth of data that would be so cool to have. Yeah, there's a rejoinder.
So we are getting more and more obsessed actually about productivity at Meta, and that is what we now have to use to justify work on programming languages. And that, so we have to argue why static typing, say, is going to improve programmer productivity, or some IDE feature or whatever. So it's a kind of interesting place to be now, because we can't just say, yes, obviously it's the right thing here, and just appeal to general trust in programming language folk. We have to actually justify in terms of productivity.
So give us the data. We'll help, right? I mean, we have armies of unused grad students who are currently, finishing their POPL papers, but we could retarget.
Okay, I think we are done for this session. Thank you so much, Jan, one more time.